Good evening. Can you hear me? We will wait for like 5 minutes, then we'll start the session. I'm waiting. Let's wait for others to join. I will go through a small presentation of last week's sessions. Like overall, it covers bioclimatic assessment, thermal performance of envelopes, and also glazing. The final part of the thermal envelope I will cover it in the next session. Uh, the final part of the glazing, which includes okay. Let's start the session. Like, is it possible for you to like switch on the mic and introduce yourself so that like I'll be able to like get to know well. If not, let's just let me share the screen.
Good evening, sir.
Good evening, Anurag.
This is Anurag Upadhyay.
Yes.
I am working as assistant architect in
Okay.
Delhi Development Authority.
Mm-hmm.
I have pursued bachelor's in architecture and masters of technology in construction technology and management from NIT Karnataka.
Good to know.
And I have visited IIT Roorkee and meet uh, sir.
Mm-hmm.
And there I got to know about thermal comfort and,
Mm-hmm.
uh, and the building science of thermal comfort, thermal adaptation, and from there I aspired to get or aspired to attend this session
Yeah,
in
it's
this
good to
course.
know. It's like thermal comfort and the performance related to the building is a major factor related to like how building is designed also. So it's very good to know that you are like inspired by the series. Thanks for joining this session. So
Thank you, sir.
yeah, last week actually I think three of you didn't join. Last week I have some. I hope that whatever recordings like on these meetings will be recorded, and then I think a video will be uploaded. It has been uploaded in YouTube. It will be shared further. You can also refer that videos if needed.
Yeah, I was not able to join the first live
Yeah,
session.
it's fine. You can ask the doubts also. I'll try to
Hmm.
clear it in this session, or else I will like come back next week and then also try to solve it.
Oh,
Let me
sure.
just, yeah, let me just start the session. I'll just go through a small presentation, and also I'll show some tools, online tools which you can use apart from the software climate consultant, which you would have seen in the
Yeah,
first week. Yeah, first session. Yeah.
the climate consultant, the EcoTech, and the solar tool by Autodesk I already used
Yep.
as demonstrated by the sir.
Yep.
So that's, yeah, that's I've already touched as sir has shared discussed in the class.
Mm-hmm. Fine then. So I'm just like continuing from the last session, like previous week, first week one, we kind of the final session ended related to thermal comfort models, where there are like multiple models. Like the first one, formula shows the ASHRAE 55, which is based on the operated temperature and a certain constant value. The last portion, what you see is the tropical summer index, which was devised in by CBRI, Roorkee, and it is based on wet bulb temperature, globe temperature, and air velocity. These all combinedly give a indexed value, which you can refer whether it is like comfortable or not. Further moving on, uh, the week 2 starts with this bioclimatic chart. Bioclimatic chart is based on air temperature and relative humidity. It was devised by Victor Alge, as you know before, and it kind of gives a pictorial range, like where you are lying. Like when you take one instant of time and then you measure the air temperature and relative humidity, whether that condition is comfortable or not, and if not, what can be done, like what kind of measure that can be taken. That's what this chart gives. So if you see like the left portion, I think you will be able to see the arrow. Like this portion, it kind of like it's more kind of a hot and humid place where you need more of ventilation and solar shading. This dotted red line shows where you separates you between where you need sun and where you don't need sun. The above the dotted red line, you don't need direct solar radiation. Further moving on, we look into this Guyon's bioclimatic chart. This chart you can actually access via online. I'll again stop sharing and reshare the screen with opening another site called as Andrew Marsh. I hope you can see. Okay, sorry. I'll just reshare the screen. So this is the website I was speaking about. This website has like various tools which you can go through. One of which is like psychometric chart. In terms of shading analysis, there are multiple tools also. And last week I was speaking the tool on 2D sun path and 3D sun path. You can explore this. These are all free tools, which is very useful. When the course was prepared, this was not functional, but this one is very useful tool. I hope you all look into it. Okay, speaking of this bioclimatic chart, yeah. So when we have a like temperatures beyond the thermal comfort zones, there are like various strategies you try to incorporate. Let me just insert a weather file. Let's take Ahmedabad as an example. So I have plotted all the hourly data, and you can see the spread. It is like spread throughout, like away from. There are so many areas which fall away from comfort zone, and mostly you can see that some portion of the is scattered. Some hours, most of the hours it is scattered just by natural ventilation, and there are some portion where you need to provide air conditioning and dehumidifying to be comfortable. And the winter seasons, like there is not much active heating required, just by giving internal heat gain, utilizing internal heat gain inside the envelope, you will be able to like achieve the comfort. That's what this whole chart shows. Further moving on, I'll also show other the other like indices and models. This is ASHRAE 55 model, which shows the comfort range, but this whole model is also dependent on other factors like air velocity, clothing, metabolic rate, and heat mean radiant temperature. So example, I'll try to decrease the clothing level. You can see that there is a shift in comfort zone also. Even when you increase and decrease air ventilation or increase and decrease the metabolic rate, you will be able to see that there is shift in comfort zone. So this you have to keep in mind. Like example, if you have just an office or a residential building, office you will have something like, for Indian condition, imagine you have like a formal attire, a shirt and pant with shoes. You can consider like 0.65, 0.6 clothing level, and metabolic rate you have seated under sedentary activity of like metabolic rate you consider as 1.1. ASHRAE 55 shows a comfort range between 30 to 34 degrees Celsius, and it's slightly like in a left side declining angle. It's that one is like it's a combination, right? Like the bottom portion shows the dry bulb temperature, and the curved lines show the relative humidity, and the right side is actually the absolute humidity. These tools you can explore, and also you will be able to see this select. If you go to the select metric data, select display metric, you can also put filters. Like example, if it's an office building, you can also filter like what time the building will be actually utilized, and this will further you can like reduce the number of points and then look into strategies which actually matter during the hours the building is operated. Finally, like all this thermal comfort related stuff is like we are speaking because it deals with building human. So if there is occupant, when there is occupant, he is utilizing the space, you can like narrow down into that particular time frame and then design accordingly. Even there are like multiple spaces within a building also. There are some spaces which won't be utilized during a portion of time. So this strategy can be used for at a space level instead of a building level also. You try to explore this tool further. I'll go back to the presentation. uh, and also there is, you would have come across this psychometric chart. Let me just speak about the process, psychometric process. Imagine you have this point, the center point of all these arrows. So if you move further from the point in different direction, if you want to move from that point, what is the strategy required? So example, if you want to like just cool the space, just reduce the temperature, dry bulb temperature, you have to utilize sensible cooling. If there is sensible cooling, there will be just reduction of dry bulb temperature. Imagine if you want to like, if you are in a, also it you can think in the other side also. Imagine there is, you have to like, you are in this point and you want to like go into thermal comfort zone. So you have to utilize dehumidification and cooling. Same way, if you want to like heat a space, you are in like in this point and you want to like go achieve thermal comfort zone, you have to utilize dehumidification and also, sorry, let me correct it. In this place actually it is dry and also cold, so you have to like utilize heating and also humidification. So there should be a proper understanding of the psychometric process so that you can devise strategies accordingly. Multiple strategies work using active means and also passive means. Example, this humidification, you can utilize evaporative cooling strategy like placing a water body nearby. That helps in humidification and also cooling. But if you have to like dehumidify a space and also cool it, you need to go for air conditioning, mechanical air conditioning. This understanding should be there. Further moving on, let's look into the envelope related factors and heat transfer factors that are related to thermal performance of the building. The heat transfer depends upon the temperature difference between the surface and the surface area of that actual element or assembly that you are considering. The surface characteristics, characteristics in terms of conductance, uh, and other multiple characters. I'll talk about it later. And there are two things that you just try to, in terms of conductance, the conductance is heat flow property of a material with a stated thickness. And if you think about conductivity, it is the same heat flow property, but it's of unit thickness. This you have to take into consideration when you try go for calculation and all. And further moving upon, this conductance and conductivity and all are actually properties of a single element. So if you go for a multi-layer wall assembly, you have to take into consideration of all conductance properties of the elements and also the heat transfer coefficient of the air layer of inside and also outside. So this thermal transmittance is actually, it speaks about a component, not just a single element, the whole component of all component it speaks about. In order to calculate it, we can just look into a small example. Imagine you have a wall, a multi-layered wall, and it has, correct me, this 120 brick wall masonry, and then a 50 air cavity, and 100 concrete, and then you have another 25 of glass wool, and then another final outside layer of 12 cement plaster. And also the both side of the wall will have this heat transfer coefficient, thermal transmittance of convection is there on both sides. Here in this example, we speak in it as resistance have been given. Basically, resistance is reciprocal of the transmittance value. So, how to find it? Here, the wall thickness have been given, and also thermal conductivity is also given. So, in order to find that conductance, you use the conductivity and also thickness. In this case, in order to find thermal transmittance, we are just trying to deduce resistance. The first layer is actually 120 mm. In the question, it is indicated as 114. So you actually divide this actual the 120 mm divided by the conductivity. You will get the resistance of that particular layer. So for all layers, you divide the actual thickness divided by conductivity. You will get the thermal resistance. Finally, you add all the resistance values, and you will get a total resistance value. And in order to get the thermal transmittance, you take reciprocal, and finally you will get the thermal transmittance value. Further, this thermal transmittance property is actually a property of conductance, and there are other ways heat can transfer, which are the other two are convection and also radiation. Convection is based on the fluid air movement related heat transfer, and convection it can be either free convection, which is based on temperature difference of the fluid. Like if you have like temperature at floor level, the temperature is 30, and then the at like roof level you have the air temperature is around like 33. Due to the temperature difference, actually there is a movement of air. This movement is actually also used in stack ventilation strategy also. This you can look further into literature. Other convection is post convection. Next, the radiation part. Radiation is basically the heat transfer by electromagnetic waves, and this heat transfer is based on the actual temperature of that whatever object it is. Here in this, I have shown a tungsten bulb where actually the tungsten filament is actually radiating heat energy. It actually instead of more than the light it is producing, the heat that it produces is high. This radiation is actually a major component because the whole heating of the building is due to the solar radiation falling on the building, and then the radiation is further like kind of absorbed, and then it affects the building also. And the other part is the air temperature. Air temperature is also due to the radiation. The atmosphere get heated up due to radiation, and then there is a certain temperature that is created because of it. This further affects the building. When we speak about radiation, two properties we have to look into. One is absorptivity and other one is emissivity. Absorptivity is a response to the short wave radiation that is falling on the surface. Emissivity is basically once a material absorbs the radiation, it starts emitting back. This emission is mostly in the long wave radiation spectrum. So this is the property related to the material only. When we take about this black body, perfect black body, it's a very good absorbent of heat, and also it's a very good emitter of heat also. This you would have come across in the week 0 assignment question. Further moving on, when we talk about insulation, there are like multiple types of insulation. One is resistive, which is a property of conductivity. The next one is reflectivity, where it's like you can directly like it's a radiative property where like the solar radiation is falling, it directly gets reflected. Another one is capacitive insulation, where it depends on the solar heat storage. Like once the heat is transferred inside a material or assembly, the capacity, it has a capacity to store a heat for a while, which is given by the capacitance. And these all properties we further look into different levels of the assemblies. Here, like when we talk about thermal efficiency, there are like 3 different levels. One is that elemental level, which I spoke about earlier. The elemental level, the property that is associated is the thermal conductivity. And another one is component level, where we have like multi layers of elements. And this is, we can speak in terms of thermal transmittance and also thermal heat capacity. Further, there is when you go to like a larger assembly level and also building level, there are other indices which come into play, so that we can use the indices and utilize them and see whether that the indices indicator is a good indicator of to achieve like a good thermal performance inside the building. Before I was speaking about heat capacity. Heat capacity is kind of it's a property based on the density of a material, specific heat capacity, thickness, and if in order to find like there are this is simple formula which was created to find what is the heat capacity required for a particular location. Imagine you have a location uh, with the maximum outdoor temperature average. This is like imagine you take it as a monthly average maximum temperature. It is 39 degrees Celsius and the minimum average temperature is 28 degrees Celsius. And also you have to you should know about the absorptivity value, which we saw earlier. Absorptivity is the amount of radiation that is absorbed by a surface. And the other one is I max is the total, like it's the maximum amount of radiation that is like incident on a surface. This you can find from weather data 39 and 28. This maximum and minimum temperature, average temperature, this you can find it from the weather data. And the absorptivity is based on the surface. Example, you have outer wall surface, you find the absorptivity based on the surface treatment, like whether it is like painted white or like, it depends on the surface level treatment only, the absorptivity. Then you can actually deduce the required heat capacity of the whole wall. In this case, the required heat capacity is around 65.75. Further, there are like multiple performance indices which you can see now, like ULE, which we spoke earlier. This is ULE, it's at component level. Thermal damping. Thermal damping is more like a building level or assembly level. It is based on the difference between the maximum outdoor temperature and the minimum outdoor temperature minus the maximum indoor temperature minus the minimum indoor temperature divided by the difference in maximum outdoor temperature minus the minimum outdoor temperature. This gives a indicator of like a certain value, and it should be minimum 60. The thermal damping value should be minimum 50. This is set by National Building Code. And there is another indicator called decrement factor, which helps you to find that, like, it's also an indicator like you would have come across in the previous sessions in terms of time lag. Time lag is basically the total shift in the peak temperature. Like, what is the difference in time when there is between the peak outdoor temperature to the peak indoor temperature? That is time lag. And decrement factor is also an indicator. Both this time lag and decrement factor are indicators of the thermal heat capacity. And this thermal performance index is actually an indicator of the inside surface peak temperature. And having a thermal performance indicator less than 75 is deemed good as per same standards. Now, another index is the thermal time constant, which is a summation of all the total heat gain divided by the thermal transmittance value. And this you would have seen this table, which is from SP41, which gives recommendations of the U value, thermal performance index, thermal damping, all these values. What is the recommended roof and exposed wall value for hot and dry climates and also warm and humid climate. There is another index called building index, which is the total maximum heat gain averaged over entire surface area of the building envelope to the acceptable limit of heat gain for achieving comfortable conditions. And it's basically, if you have a building index value less than 50, it is the space is considered comfortable. This is as per the SP41. Further moving upon, these all properties before we were speaking, these are all for opaque materials, basically wall and roof. Next, we have to look into the properties, what and all properties we have to consider for glazing. And the glazing's thermal performance is basically depends on the thermal transmittance value of the glass separately and also the frame material. So we have to think in terms of the U value for both the glass and also the frame. And the next one we have to consider is the solar heat gain coefficient. Like before solar heat gain coefficient came into place, U value was actually only used, but solar heat gain coefficient is a very good indicator of the thermal performance of the glazing system. Another final factor that actually affects the thermal efficiency is the airtightness of the whole assembly. And looking at the thermal, the solar heat gain coefficient, it's basically just the total heat gain that is admitted inside through the glass divided by the incident solar radiation. Basically, it's just a fraction. And if you have a very less fraction value, it means that you will have very good uh, thermal performance of the glazing system. And it's totally different from the uh, visible spectrum. Like the lighting efficiency is based of the glazing system is calculated based on the visible light transmittance, and it is totally different from solar heat gain coefficient. So it is totally possible to have a very high thermally good thermally performing glazing system with also good VLT value, and this improvement can be made using low E coating, and also if we try to reduce the solar radiation which is falling on the glazing only, that will also improve the solar heat gain coefficient. Basically, if we provide proper shading with good performing glazing system, it will increase the solar heat gain coefficient. Moving further, the the final week's final session would have covered about shading angle and shadow angle and also shading devices. There are like two shadow angles, horizontal shadow angle and vertical shadow angle. Horizontal shadow angle is to determine the projection of the vertical shading device, and vice versa, vertical shadow angle is used to devise the horizontal shading device, and these can be calculated based on the solar altitude and azimuth angles. This we will discuss further in the next session because like it kind of a continuum. I am done with the presentation. So if you have any doubts related to the week 1, you can ask now. Thanks for listening. Either you can type it down in the chat, or also you can just switch on your mic and ask if you have any doubts related to the week 1. If you, or else if you want to like show further how the tool works, I can show that also. Like, can you please like switch on your mic and then give your feedback? I hope like everyone can hear me.
Yes, sir.
Yeah, thanks. Do you have like any doubts related to like the week 1? Like, this is also like the session is basically created for the learners to, if they have any doubts, they can ask in this session. I'll try to like clear it.
I had a doubt from the second week
Yeah, please.
regarding convection. How we consider convection factor in our thermal comfort calculation or building design solutions?
Okay. Mm,
How we
convection,
address the convection factor?
yeah,
How we
convection
address it?
factor. So how we address is like one thing, convection helps in achieving thermal comfort. When we consider like if you have a person inside a building and then the temperature is around like 32 degrees Celsius, when we look into the first week's topic where you can increase the comfort range by utilizing air velocity. That is one way. Another one is in this particularly related to week 2. This convection part is basically heat transfer inside the building through convection. So the heat inside the building can see like can enter the building via this infiltration. Like if you have air gaps in the building, like where you have this door and the window, there will be like small air gaps. Through these air gaps, and also when you operate the building, also like when you open the window or close the door, open the door also. When there is like difference in temperature between the outside and the inside, automatically there will be heat transfer via convection. Basically, that will come inside the building. So that is one major convection related heat transfer. I hope I answered it.
Okay, so for convection, like we have to maintain the densities also, the air densities
No,
inside
air
and
density we
outside.
don't mind. Only thing is like if you maintain this air tightness, we were speaking about air tightness.
Okay, so there won't be any leakage of
Yeah,
air.
yeah. Basically, you imagine you have a condition where it's like you need dehumidification and cooling, where you have to run an air conditioner and you start conditioning the space. If you have this infiltration gaps via convection, the heat will start transferring from the outside and come inside come inside. So there won't be effective cooling that will be achieved inside.
Okay.
Yeah,
So in the slides you have shown
yeah,
where you have discussed that question on
mm,
U value.
yeah, yeah.
Uh, in there that in the solution you have said to divide the thickness by thermal
I'll just
conductance.
yeah, I'll just go there. Yeah, yeah, this one, right?
So here you are dividing thickness by thermal conductivity.
Huh.
So isn't
This
the
this will this
conductance
will
is
yeah,
conductivity divided by thickness?
yeah. But what we are trying to find out is the resistance. I have written resistance here, right?
Okay, okay.
Like basically, you cannot just directly find the thermal transmittance like just by adding values. You have to like first find the summation of all the resistance values. Then you divide, like take a reciprocal of the resistance. That's why here in this case we are finding the resistance value.
Okay, okay, okay. Got it.
Yeah. Yes. Purnima.
Yeah, sir, I am actually a research scholar. I'm working in thermal comfort zone. Uh,
Okay.
I'm working in the topic. I wanted to ask about solar temperature.
Uh-huh.
Yeah, so is solar temperature measurable, like directly measurable with some equipment or?
No, it's not directly measurable by equipment because it has like two different things in we have to consider, right? One thing is the absorptance value of the surface that you are measuring,
Surface?
which you
Yes.
cannot like measure directly. You should know
Okay.
the absorptance value. Maybe
Yeah.
you can kind of reduce it further, like not directly using single measurement, but
Okay.
that you can. And another one is
Uh,
the radiation. Radiation is dynamic that you can actually measure it.
Measure it. Yeah.
Yeah.
So radiation actually, if I measure it right next to the wall, or because I cannot really measure radiation if I'm keeping a equipment on the wall, right? Like.
Mm-hmm.
So is it if I place something like something that measures radiation right next to the wall, will I can I use it as a because
Yeah,
I'm talking from a
you
research
can.
point of view.
Yes, yes, you can use it.
Okay, 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 and I can use heat flux meter or something like that this kind of a thing that is a heat flux meter which
Yeah,
measures
heat
the
flux
heat
meter
through
you
it.
can also utilize it.
Okay, okay. So with these things, I can actually I can do this thing and I have to calculate it manually.
Huh.
Yeah, is there any software that I can use it? It's not really directly my field. I'm working
Simply,
on.
simply all like if you just have to like throughout a year, if you want to find out, you can take the weather file using the utilizing the weather file. You will have this average radiation that is falling
Yeah.
using the. But you have to like also check based on which orientation it is, like the orientation and also the radiation that is falling.
Okay.
You will have this I value,
Okay, okay.
and
Okay.
absorptance
Yeah.
value you will have it will be based on the surface.
Okay, okay. Yeah. Okay.
Now,
Okay.
all that is left out is the outside temperature. That is also you will have the dry air.
Yeah, so like if I use a simulation software or something which gives me the surface
Mm-mm,
temperature,
mm-mm,
I can use it for like it might not be very accurate, but at least for um, study purposes, like if I'm studying for orientation or for a different type of wall surfaces, for example. So
mm-mm. Yeah, it will be
um, yeah,
helpful.
okay, okay, yeah, but okay, okay, but there is like I cannot do it experimentally, like completely experimentally, where I can
You can do it experimentally. Only thing is like,
with calculations only.
yeah, you have to calculate it finally.
Okay, 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 okay.
It's
Yeah,
not like
that's okay.
directly
Okay.
measurable like heat stress meter
Heat
where you
stress. Yeah.
get the
Okay, okay.
W wet
Okay,
bulb
okay,
envelope
okay.
temperature.
Okay, got it. Thank you.
Thank you. That maybe I'll show the tool again. Is it fine? Like, were you able to like get what like since you are online, try to like maybe check this Andromas tool that I mentioned. If you have any like, there is you don't won't have much doubt and all. It's just like a easy tool. You can just explore it. I'll just reshare the screen and show that. In this blue lines actually depict like the monthly ranges, like temperature, the conditional condition, the thermal condition ranges, the maximum and the minimum ranges. So this kind of indicates like the how the diurnal range is wide or not. If there's a high diurnal range, you can utilize strategy like high thermal mass. That will be a good indicator when you choose this show months range. And this daily outline also, this is also for a single day you can like see what is the diurnal range and also what is the whole pattern also. Pardon. Um, and you can switch on this show date indicator, like particularly you can move into like particular day also or also month also, like for a whole month range you can, this will average out and then show what is the shift in the thermal condition starting from the night till next day. And also another thing, data points also you can select per month. Example, if we have this July month, here it's mostly some parts you have the condition which fall inside the thermal comfort zone, and some parts with natural ventilation you can just satisfy the condition. And one more thing is like this particular chart that we are seeing is based on the weather data, and based on the design, actual final design, you will have different thermal conditions inside the indoor also. So the final uh, output that you have to look into is the indoor conditions, how they will they are these data points actually further you can plot inside and then see whether they are comfortable also. And so basically this whole chart business is based on the outside weather data, and this you can utilize it and then choose the strategies that you want, and then you implement the strategies. And further uh, the coming next week, like this week, the week 3 and all, I think you will be exposed to thermal energy simulation of buildings, and those will yield the indoor temperature conditions. And you can utilize those conditions and then further place it in the psychometric chart and see finally where these data points are in place. So this is Ahmedabad, and you can see that like when you look into this May and April conditions, those are the times where that thermal conditions are like hot and also dry, which will require two different strategies. When the conditions are too dry, you just utilize high thermal mass and night ventilation strategy. And there are conditions where the condition is hot and also humid. When the temperature is beyond some limit where the condition is like too humid and hot, you have to go for air conditioning and dehumidification. Here, the only option to kind of improve the energy efficiency is choosing and properly sizing and also choosing a efficient system. That is the final way. And we further, when we look into these winter conditions, basically winter conditions in Ahmedabad during this actually, if you remember, I have chosen this metrics. It's 8 to 5 p.m. only. These are like office hours. During office hours, basically during winter in Ahmedabad, all the conditions almost fall inside around the thermal comfort zone. But now let me just change the whole setting. Like imagine we are looking into a house where like a person is like working and then he comes back in the evening and then starts in the early morning. The condition actually totally changes. Like here, it's the condition is more colder in the winter time, where you need some kind of internal heat gain. Basically, if you have like uh, the high capacity wall and then the heat which is uh, basically the solar radiation in the morning time and the afternoon time is stored in the wall envelope, and further it will be kind of re-radiated inside also. Like basically if you have a wall, it kind of re-radiates in both direction, so you cannot say that the heat will be dissipated easily. It takes time to like it dissipates very slowly. And if you look at the right side, in this you can see that like the cooling strategy basically involves two parts when you have a high capacity wall. One thing is you should have a high capacity wall, and also you should have night ventilation where you try to like flush the whole building. That is one main thing you have to consider. So let me go and plot the whole year only.
Sir, what is this 19 degrees Celsius line?
19 degrees. Basically, this given is bioclimatic chart, right? It is based on the
Hmm.
mean outdoor temperature. So if there is change in the temperature, if you're indicating, the whole strategy shifts. When you go to this PMV based overlay, here the neutral zone, which is like which lies between minus 0.5 to plus 0.5 of the PMV predicted mean volt. Even this one shifts when you change the clothing or the metabolic rate or the mean radiant temperature. Because the PM value is based on 6 different factors, as you remember. So changing each value actually affects the predicted mean vote. So if we have predicted mean of weight was 0, it is like means like it's a thermally neutral condition, and this thermal neutrality is based on an experimental setup, and it's kind of like different from actual field study. So PMV is kind of like more kind of a it you can't say directly that if the PMV is 0, a person will be comfortable. Maybe the person will be feeling a bit cold also. Imagine like the mean radiant temperature is like 26 degrees Celsius. It's like clothing is like 0.6 and a person is like seated and in a relaxed position. Here this PMV is indicating the neutrality is shown around 35 36 degrees Celsius. Maybe in this based on the formula it is showing that 35% will be feeling comfortable, but at 35 a person might say that he is feeling hot. So all these actual like charts and indices basically it's based on a set of data set, and then they have determined it based on it, and it might not be a perfect match, but it is a good indicator that you have to remember. Other than this, there is another chart like instead this is psychrometric chart, there is another chart called as relative humidity chart, which is like it plots dry temperature on the x-axis and then relative humidity on the y-axis. What else I can show you? And here you can also like apply filters. Like example, you want to see how many hours are like how much amount of data points are falling, like where the dryable temperature is like below certain threshold temperature. Example, if we have any dryable temperature below 28, you want to find like you kind of set a condition that whatever temperature, dryable temperature, which is below 28 degrees Celsius, will be like a comfortable condition. So these many hours will be like will fall below the 28 degree range. This kind of filters you can apply and also utilize, and there is also an option to export this chart for further presentation also. I think that's it from my side. I'll stop sharing the screen. Any other doubt if you have, you can ask, or else we can close the session. Next week I'll cover the week 3's portion, which is related to, let me check. It's about thermal simulation and also lighting. We'll look into it further. Is there any other like feedback that you want to give related to the course? You can also give. I'll try to push it forward. Fine, then thanks for listening.
Thank you, sir.
Thank you, sir.
Thank you.